All right, I'll begin. Dear Father, we thank you for this morning. We thank you for the weekend just completed. I just pray again that you'd just guide our thoughts today and just help us to glorify you, Lord, in what we do. In your name I pray, Lord Jesus. Amen. All right, so you guys had questions about your homework, perhaps? As you can see, the earlier section is in reruns. It's more or less what we did Friday, right? So? Don't all speak at once. So you already understand the homework? I don't want to hear that. I don't even want to hear that. Them's fighting words. Given the time you've spent on the homework already at this point, what well thought out questions have you found to bring to me today? I will say this for I think it's problem number 26. All right, in 10.2, is it? Asks you to derive the law of cosines. So you work out 25, you get this formula, right? Which I have written up there, which of course is no secret because that's 25. It's an odd problem. The answer's in the back. So you work it out. But to see the law of cosines, really you just need to, decide on a good target. So like my target is this. This is, for me, in red, the sort of canonical law of cosines, ABC triangle, not necessarily right. Theta is the angle opposite to C, right? And the statement of the law of cosines is C squared is equal to A squared plus B squared minus 2AB cosine theta. And geometrically, I believe you can safely say it's assumed that theta is what? Between 0 and 180. I suppose... What's that? Yeah, I guess when theta is 180, it might still make sense. I don't know. What's that? Well, C would be A plus B, and A plus B squared is A squared plus B squared plus 2AB. From sort of the perspective of continuity and logic, it would be weird if the limit of the law didn't make sense. I mean, yeah, it's not a triangle anymore, but it should still say something that's kind of like logical, right? And it does. Yeah, a degenerate triangle. Yeah, we'll try to kick those out at the border or whatever. Oh, I'm sorry. So insensitive of me. All triangles should have a seat at the table. Sorry, I heard some funny Bernie Sanders jokes this weekend that amused me. I will not share them with you. All right, let's see here.
At this point, what is worse?
What is worse? What is worse, Bernie Sanders, or you're asking the question of which is worse? Oh, I can't even. Well, yes, I have to be careful with what I say. Some things I'm not supposed to say. So. Yeah. That's right. I have to make sure I keep this a safe space for you guys. I forgot about that. Don't want to violate your safe space. How do you convert this to a Cartesian equation? Listen, not with formulas, okay? I mean, I guess you could use formulas. Fine. If you feed, what do you got? X equals to r cosine theta, right? Y equals to r sine theta. What happens when you put minus pi over 2 into these? Right? So, I mean, but those don't entirely give you the picture. I mean, we know geometrically what this is, right? Well, I guess that's the question. Yeah, see, this is one of the reasons I really do not like allowing for negative radius in some senses. It adds an ambiguity to this question, which I don't care for. In my world, past Calculus 2, where we don't look at silly graphs of polar equations with negative r, that's this. There's no ambiguity. It's that. It's the ray that goes to, that's it, right? If you allow for minus r, it also includes the other direction, right? Because allowing for minus r takes every graph that you make and it inverts it. It adds a copy of it on the other side. So like you can see this, y is equal to minus r, right? If r, so y equals minus r, and if r is an element of the reals, well this gives you what? Whole y-axis, right? So what's the answer? Is it the y-axis or is it the ray off to, is it just the negative y-axis, you know? Yeah, I mean, if we allow negative r, it's the y-axis. But if we don't, it's not. In Calculus 3, for example, if I said that theta was equal to minus pi over 2 and you told me it was whole y-axis, I would want to throttle you. Like, I would not be happy with you. In Calculus 3, when I talk about polar coordinates, I personally do not allow negative r because it's geometrically confusing. You don't want a degenerate description of points, you know? And yet, we're in chapter 10, so we're stuck with following the book, and we have to allow for negative r, and that's the world we're living in at the moment. I'm just warning you, as you leave this course, you should put away childish things and forget about this negative r business, all right? Just saying that. Okay. Sorry, I will stop complaining about the negative r. It is what it is. Wait a minute. I don't recognize you. A visitor. Are you're not enrolled in this course, right? Okay, just checking. You don't have to tell me. You're welcome here. I will stop drawing attention to you. Yes?
How do you represent, when you had polar coordinates with a negative r, how do you represent that not using a negative r? If you just had like polar coordinates -1 pi over 2, then how would you?
I wouldn't allow -1 pi over 2 if I was. What do you mean? I mean, if I don't allow negative r, I don't allow -1 comma pi over 2. You're saying r is equal to -1, right? That's not allowed. That's the point. R is equal to the square root of x squared plus y squared for an ever and ever, amen. So be it. That's it. End of story. Square root of x squared plus y squared. And we have all the angles we like to go from 0 to 2 pi. So I'm not sure I understand your question yet.
I guess I just know sometimes when you'll be given a coordinate that has
Oh yeah, well if you're given a coordinate that has a negative r, you're stuck with it. You're in this infantile world of chapter 10. You have no choice but to deal with it. I mean, it is what it is. You know? You know, it's like when you're asked a loaded question by a reporter, you have to like respond to it. And if you're not enough time, then you're stuck with whatever they said. So. Okay. Other questions? Actually, there hasn't been a question asked yet about the homework. Oh well, I'm going on. So, arc length. So I've showed you, somewhat heuristically, not really. I mean, I gave you a specific definition of it, how to calculate it for a path. There's certain fundamental issues that I haven't dealt with, right? Arc length, it should be something geometric, right? So I gave you this formula that's based on calculating it from the parameterization of a curve. Well, I've also told you in the same breath that a given curve has infinitely many parameterizations. This begs a somewhat unsettling question. What's the arc length, right? But the trick is that if you reparameterize the curve, if you look at two different parameterizations of the same point set, you'll get the same arc length. So there's a theorem that says that the definition I gave you, despite its apparent dependence on parameters, in fact independent of parameter. There's that. So let me try to define things a little bit more carefully from the start. So first of all, given curve C from, say, point P to Q with path R of t such that R of A is equal to well, I'll tell you what, I'll say R of t naught is equal to P and R of T1 is equal to Q. So here's the picture. It's something like this, whatever. Here's your point P, here's your point Q. A typical point somewhere in between is given by R of t for some t between T naught and T1, all right? Given all this, we define what? You can define the arc length at time t. The integral from, say, T naught to T of what? The square root of, well, I mean, there's different ways I can write this. I'll write it parametrically. You could say dx. I'll even use a u, so you guys are not bothered by the tau. dy du squared du. This is the so-called arc length function. And the path is given, it's got x, y. So, like R of u is x of u, y of u. These are functions of u. This defines the arc length function, all right? We calculated it last time for a circle. There's a pretty obvious theorem that you get from this, right? Theorem ds dt is equal to what? What happens when you differentiate the arc length function? Fundamental theorem of calculus part 1, right? You're differentiating an integral with a variable bound, so it just pops back out. Square root of dx dt squared plus dy dt squared, right? So of course this is also the speed, right? AKA magnitude of what? Velocity. But I suppose, that's nothing wrong here so far. And I could prove to you that if we took a different parameterization, a so-called reparameterization of this curve, you'd in fact get the same arc length, all right? But I think I'll leave that to Calculus 3. If you want to see the proof of it, if you look at my Calculus 3 notes, it's in there. Basically, you just say that, basically do like we did last time, remember? We replaced t with s over r, and then the new curve had a, the chain rule pulls out like 1 over r. Well, that kind of thing happens more generally in such a way that when you differentiate the reparameterized curve, the chain rule pulls out this basically like change of speed factor. And then when you integrate that, the change of variables, like U substitution theorem, says that the two integrals are the same just because basically your reparameterization produces a change of variables of your original integral, and so you end up with the same integral despite the fact that you've used a different parameter. Heuristically speaking, though, of course, you could also look at this as, well, what we're really doing is like integrating ds, right? So ds is ds dt dt. And so like to get the total of ds, I'm just integrating this, right? And so it shouldn't matter which t you use because you're just really finding a way to calculate ds, right? And ds is independent of t. That's a heuristic way of thinking about it. But erase that. Anyway, there is something that's missing from our discussion so far. I'll leave it. Which is, I haven't really proved, let's say, that this thing I'm calling arc length really is the arc length, right? And so there's something more basic we could do to try to understand this. And it would be something like along the following. So let's try to derive arc length for smooth curve from a limiting process. And so people who are more careful or better teachers, whatever, however you want to think of them, they might have started with this. I didn't start with this because I don't think students are super interested in this, and I think a lot of students get lost in what I'm about to do. But nevertheless, it is part of the discussion. We should have it. If the class wasn't doing well, I might omit this from the discussion. I think you guys are doing pretty well at the moment, though. So we have some path, all right? We have some path. We can describe it parametrically, all right? And the question is, what's the length of this curve, right? So, what would you do? I mean, I think the first thing you might try is to calculate the length of something else you already know how to find the length of, right? What do you know? What if we, instead of looking at this as a smooth curve, we approximate it, right? With like some interpolating points. So, and I'll keep it relatively simple. So this would be like T1, T2, T3, T4, and then finally Tn. Okay, Tn minus 1. So there's a break in the story here. All right, here's T5, whatever. See, if you connect the dots, right? And I'm supposing that they're equal time. So, and this is for a given curve like I was setting up over here. So C from P to Q. And you've got R such that you're basically taking the interval from T1 to T2 and you're mapping it to the curve C. So what I'm trying to say is that, say T naught. So this T naught has R. R of T naught is equal to my initial point P. R of Tn, well, Tn is equal to T, oh, unfortunate language. No. I need something else here. I'm sorry, I'm going to have to go back to A and B because I don't want to have any, I'm sorry, I'm going to have to use A and B here just to have different, I don't want to connect it to this enumeration of the T's. So let me use A and B. So like R of time A, the initial time is P, and then like over here we have Tn is equal to B. And so like R of time B is equal to Q. That's the final point for the curve, okay? So we're going from point P to point Q. We've got this path. So far so good? And what I'm suggesting is we could take this path and we could replace it with its, like connect the dots, right? We all did this when you were younger, right? Remember these? Taking you back to a simpler time. Let's see here. You say we wish you could turn back time to the good old days? Uh-huh. Interesting. Let's see here. I do wish we could do that. Let's see here. Okay, so you can see, and like, so let's see here. The T sub j would be equal to A plus j times delta t, right? Where the change in time between the, I'm taking equal time increments. So the time increments would like be B minus A over N, right? The number, and I guess, Right, yes, that's right. So like T1 is A plus delta T. Okay. What's the length of one of these arc length? What's the length of, like if we say that this is L1, this is L2, this is L3, here's L4. How many are there? This is the nth one, right? So the total length is what? Natural log. Why? Oh, that's awful. Let's see here. It's worse than my jokes. Let's see here. L1 plus L2. Ooh, no, that's cold right there. Let's see here. See L4. Eventually you get to n, right? The sum of the lengths should be the total length. Do you guys agree? When it's smooth enough. Well, I mean that there's no disagreement that the total length of the red curve is that. I mean it's not smooth, but we still agree that that's its length. Smoothness of the blue curve will come soon enough, but we'll see. Okay, so how do you get those though? Like, what's the length? If I focus in on the jth one, what's it look like? You got two things going on, right? You got the change in x in the jth direction, and you got the change in y in the jth line segment, right? So like change in x should be what? It should be x of tj minus x of tj minus 1. And the change in y should be what? The jth change in y should be y of tj minus y of tj minus 1. Agree? I mean, that's, for example, to get the first one, I would take like x1 minus x naught to get the change in x, y1 minus y naught to get the change in y. And so in particular, you have what? The length L sub j should be equal to what? L sub j should be equal to the square root of the change in xj plus the change in yj squared, right? Do you agree? I mean, I hope you agree. So if I want I can recapture this. This is really the total length of the red curve again, is the sum. What do we got? We got the sum j equals 1 to n of the square root of change in xj quantity squared plus the change in yj quantity squared. And of course, we could write that in more ugly ways in terms of the actual x of t and y of t, all right? Now, now here's where smoothness comes in, okay? If you take the limit as n goes to infinity, what should we get? If you think about this, taking shorter and shorter line segments, we should get closer and closer to the blue curve, right? So like geometrically, it should converge to the same thing, and so that should give us the arc length. But what I've just written isn't anything particularly nice as you take the limit as n goes to infinity. I mean, we need to rewrite that in some way that we can actually calculate it, right? So what you do is we just apply the mean value theorem. Apply the mean value theorem. So how about the mean value theorem? Mean value theorem. Okay, so we have x is a function from, let's say, tj comma tj minus, well, I'm an idiot, tj minus 1 to tj, right? To the reals. And likewise for y. I mean, this is the jth x. Well, I'm sorry, the x, you can restrict x to this interval, right? And says that this is a smooth function. Smooth function, so that says that it has derivative and it's continuous. What does the mean value theorem say though? In particular, it says that there exists some, let's say, t sub j star. Yeah, that's between, that's somewhere in here, right? Somewhere in this interval, such that what? The average rate of change is equal to the instantaneous rate of change, right? At t star. That's what the mean value theorem says. It says that if your function's differentiable and then over some closed interval, then you can find a point in the interior, or possibly, I mean, you could be at the endpoints, I suppose, of the interval, such that, where'd my thing go? The instantaneous rate of change is equal to the average rate of change. So let's see. In other words, it allows me to rewrite delta xj as what? As dxj dt, right? At the point tj star, which I don't know. I mean, the theorem gives me that. It doesn't tell me which one it is. Just know it exists, right? Times delta t. There's no j dependence on the delta t because I chose a partitioning of time of equal time increment, right? And so check it out. And you can do the same thing for the y function, right? You can apply the mean value theorem to the parameterization of the y coordinate as well. And so what you get then is that our nth approximation here can be rewritten as the square root of dx dt dx dt at time tj star squared same thing with y dy dt at the tj star. It doesn't have to be the same one though, right? I should probably be clear. Let's say tj star star for the y. It doesn't have to be the same time increment logically, right? And then we get, what else do we get here? We get a delta t squared on both terms, right? So if you think about it, you can do what? You can take that delta t squared and factor it outside of the square root, right? Delta t is by construction positive. And then what happens if we take the limit as n goes to infinity? What do we obtain? We get length of the blue curve, right? In other words, the length of C is equal to the integral from what to what? This is the Riemann sum, right? If you take the limit as n, put a limit as n goes to infinity out here, this is exactly the Riemann sum of what function? Well, the square root of dx dt squared, right? Plus dy dt squared. Now there's a little bit of let's see here, from A to B, right? And there you have it. That's why the arc length has to be that formula, because if you calculate the arc length of a polygonal line approximate of a given smooth curve, you can show that the arc length is nothing more than the Riemann integral of the square root function as such. What happens to the t sub j star and the t sub j star star in the limit? They're always in the right place. They're always in the partition between t naught and t1, or between t1 and t2, and so forth and so on. That's what you need to make my conclusion that I do for the Riemann integral. Admittedly, there's a little bit of analysis glossed over there. Yep.
This is like finding the area with like the numerous increasing blocks, which is one term.
I'm really just going back to the definition of the Riemann integral, that if we have a sum which is infinite, right? I mean, if you take the limit of a sum going from 1 to n as n goes to infinity, and it's such that you have this kind of partition, right, of one variable, in this case time, of equal increments, and you've got a delta t factored out, well, go back to the definition of the Riemann integral, this is exactly the Riemann integral of that function. So I guess you could view it in terms of area, but I just wouldn't. Riemann sums, yes, they're assigned areas, sure, for a real valued function, but they're also just a continuous sum. I'd really rather look at this as a continuous sum, where we're adding together the lengths of these guys, because that's what it's actually. Mm-hmm. And this also, you might pick up on the fact that this explains why that thing I did earlier that seemed to violate Pythagorean theorem, right, which is not possible. Well, the devil's in the details there. The stair-step function that we looked at, remember, way back? The thing that makes it not follow this derivation is that it's not a smooth curve. Like that thing, remember the thing we did with it? We take it and we looked at it basically was infinitely jagged. It's far from smooth. And that's why we got a contradiction, because actually you can't calculate the arc length of an infinitely jagged curve. At least you can't calculate the arc length of an infinitely jagged curve with that formula. If you wanted to calculate the arc length of something that was not smooth, you'd be forced to think about other things. And it may be possible to think about those things. I just personally don't know them. Yeah.
You have to have a curve that's continuous on the sec1.
You have to have a curve which at least has continuous, at least has a first derivative, at least differentiable. I think that may be enough here, because I can apply the mean value theorem if I have the first derivative exists. I kind of want to say that first derivative also has to be continuous, but I don't think I use that here. But anyway. All right, so listen, guys, what do we have left to talk about in this chapter? How do you find tangents to parametrized curves, right? And of course, surface area. Which would you like to talk about first? Surface area? All right, we have a winner. I'm glad you said that, because that kind of fits more naturally with this discussion here. And then I think once I've done that, then the rest of the week I'll just spend doing example after 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 example. You get the idea of these things. In my personal opinion, the conceptual content of this chapter is minuscule compared to what you just had test-wise. There really is not that much going on here. I don't personally, but then again, I understand parametrized curves, so it's hard for me to put myself in your shoes. I remember vaguely what it felt like to not know what they were. I remember wondering where t is. Like, where's t, though? Because I was thinking t should be the same as x and y, but it's not. T is dependent on the example. All right, so here's we get rid of that. We already did that last time. Surface area of a surface of revolution. All right, and this is not revolution in the sense of Ron Paul or Bernie Sanders. This is revolution in the sense of, like, you take a curve, like this one, and then you rotate that thing, like so. Something like that. So you're taking a curve. This is so here we're actually, you can think about, taking that curve and you're just sort of rotating it around. Typical, if you have a nice table at home, right, you might look at the legs, right? A lot of those are made from turning a piece of wood on a lathe, right? And so you have the same profile curve, and it's just obtained by revolving that profile curve around that central axis, something like that. Something that's a relatively simple three-dimensional surface, right? Two-dimensional surface in 3 dimensions, but. All right, so what's the surface area is the question. Or you could ask, for example, what's the surface area of a sphere, right? You could ask, what's the surface area? Although, what would the revolution curve be here? I believe that would just be a half circle, right, revolved around the x-axis. Let's see here, another picture, just trying to get a sense of what's going on here. Cylinder, what would that be obtained from? Would that be obtained from revolving what? Yeah, just take a line segment like that, say, and revolve it, right? So how do you calculate the surface area of, oh, I think we can do this one, right? What's the surface area of a cylinder? If it has length L and if it has radius R, you guys tell me, what's its surface area? What do? You just take this thing, cut it somewhere, right? Like so. And then lay it out flat, like so. Right? That would make what? This length would be L. And what's this length? We just got done calculating it last class. What is it? Circumference, 2 pi r, right? So the area here, surface area, is equal to 2 pi RL. That's our basic observation, is that we can calculate the surface area of a cylinder with ease, right? I'm sorry? Yes, this is an open cylinder, right? If you wanted to close in the, yeah, that goes without saying. I'm sorry. Yeah, if I wanted to say cylinder with caps, I'll have to say something more. It's understood that we're not closing in the caps, so it's just this part. Yeah. Good, very, very useful comment, guys. Thank you. If you take physics 2 right now and you're applying Gauss's law, well, Gauss's law applies to closed surfaces. The cylinder without the caps is an open surface, and in fact, Gauss's law would not apply. You'd have to throw in the caps to apply Gauss's law. But anyway, all right, so that's kind of our basic building blocks. See, so I was happy that Mr. Anderson suggested this because I think it is tied to that discussion in the sense that, like, to find the arc length of a curve, we broke it up into little line segments because we know how to calculate the arc length of a line segment. That's just Pythagorean theorem, right? This one, we also want to divide it up into little things we know how to do. We know how to do cylinders, right? So, and let's see here. There'll be a more lengthy derivation of this in the book, which I'll skip. But basically, you could just kind of, actually, it's a little bit tricky. It's not actually a cylinder. It turns out it's kind of a cylinder, but it's not exactly. It's more like a bit of a cone. So like, oh, my picture is awful. Let's see here. Oh, well, I tried. So, what's that? Look like what? Well, like for this one, what I'm trying to say is what I'm trying to do is look at like a little bit of it like this revolved around. So, and then it goes around the back, you know. So what's the surface area of that little strip? I can draw it better if I just draw it on its lonesome like this. So the question is, like, what's the, let me try to draw an axis through here. So the one thing that matters, of course, is the radius, right? So you have the radius, and then also this here, this little distance right here would be ds. And it turns out you can argue this, I mean, well, it's not. It's fairly intuitively clear that the area of something like this will be 2 pi r dA, let's say, will be 2 pi r times ds. But what is that? Now, if this top profile curve, right? If this top profile curve is, what is that? That's y equals f of x for, this is where that's the function which is being revolved. So going back to what we did last time, ds is what? So what's r? Well, r is exactly y, right? And ds is the square root of 1 plus dy dx quantity squared times dx. And there you go. Integrate that thing from a to b. That gives you the surface area of a graph from a to b revolved around the x-axis. Now, now I stated it for, this is for graph y equals f of x, a less than or equal to x less than or equal to b, revolved around x-axis. Now, before I get carried away and start telling you about a bunch of other cases, let me see what actually the book does. Ooh, centroid of a curve. Exciting. I guess I should still talk to you guys about that, huh? So 10.8 is area of a surface revolution and centroid of a curve. Oh, okay, well, fine. I mean, so he also mentions that if you had parametrically, what would this reduce to? The surface area would be equal to what? The integral, say, from t1 to t2 of 2 pi y square root of dx dt squared plus dy dt squared dt. So here he has in mind something like this. So it's the same kind of curve, but just described parametrically. See, the thing that's, attracting my interest is the fact that you could take a parametric curve and you could do other things, right? You could revolve it around the y-axis. You could revolve it around another line, like y equals to 3. Or you could revolve it around like x equals to 10. There's lots of different flavor choices here. But we're going to stick to these two, I think. It's enough. If you really understand these, you can understand how to generalize them to other axes of revolution, right? So, oh man, you guys got to tell me when I'm over time. So the next thing I'll do probably in here is to calculate the surface area of a sphere. It's not going to be that bad, actually. Anyway, you can hit the stop. I got to give you guys your test back.